Welcome back to the deep dive. Today we're diving into this research paper you sent us, 1711.10306, Robust Machine Learning by Median of Means, Theory and Practice. It's all about using median of means, or MOM for short, for, well, robust machine learning. And I know that's something you've got a lot of experience with.
Yeah, definitely an area I'm passionate about.
So before we really get into it, can you give us the big picture? Like, what's the main problem this paper is trying to solve? What's the big deal about it for robust machine learning?
Well, the paper's all about making machine learning models that aren't thrown off by those pesky outliers. They can really mess things up.
Right.
It specifically looks at how sensitive some standard algorithms like, LASSO are to even a single outlier. It can really skew the results.
Yeah. Okay, so it's about making those algorithms more robust. I see the paper talks about empirical risk minimizers, ERMs. How does it connect to making ERMs more robust?
Yeah, so they introduced this idea of using median of means, this MOM thing, as a robust alternative to just using the regular average in ERM. Basically, instead of just taking the average of all your data, you divide it up into these blocks, calculate the mean for each block, and then take the median of all those means.
Oh, okay.
And that makes it, the whole thing, much less sensitive to those outliers.
Makes sense. Now, the paper dives into how sensitive machine learning algorithms can be, especially when you've got things like unbounded loss functions and big feature sets. And they talk about corrupted data. Can you give us some real-world examples of how this sensitivity plays out?
Sure. Imagine you're trying to, let's say, predict house prices.
Okay. Yeah.
You might have an outlier in your data, like, some historic mansion with a crazy high price tag that's totally out of whack with everything else.
Right.
And that one data point, that outlier, can totally mess up your model. So it's important to figure out how to deal with those. The paper talks about two types of outliers, really. The ones that are just like, errors or noise.
And then the ones that are rare but actually important, like maybe you're trying to detect fraud or spot some weird thing in a medical image.
Right, yeah.
So you have to think about both.
So how does this median of means approach help with both of those, both kinds of outliers?
Well, for the outliers you don't want, the noise and errors, MOM helps to minimize their impact so your model can actually learn the real patterns in the data.
I see.
And for the valuable outliers, it can actually help you spot them. If a data point keeps ending up in blocks with really different means, it's like a little red flag saying, hey, maybe take a closer look at this one.
That's pretty neat. So it's like MOM has this built-in outlier detective feature. Now, the paper gets into this idea of a breakdown point, and they even have this modified breakdown point specifically for machine learning. It all has to do with quantifying how robust something is. Can you break that down for us?
Yeah, think of the breakdown point as how much contamination an estimator can handle before it just completely falls apart.
All right. Like the typical mean, the average, is super sensitive, one crazy outlier, and it's all messed up. It has a very low breakdown point.
Right.
But the median, it can handle a lot more contamination. It's got a higher breakdown point. And then in machine learning, we care about more than just getting an estimate. We want to use that to actually make predictions. So this modified breakdown point takes that into account. It looks at how much contamination we can tolerate before our predictions start getting really bad.
So it's focused on how well the model will actually work, not just, some abstract number. Okay, so I get the breakdown point idea. But how do they actually use this MOM thing in real machine learning algorithms? It sounds very statistical, very theoretical.
Well, that's where it gets really interesting. The paper actually goes into practical algorithms for computing these MO estimators. Like, they propose this minimax approach, which is kind of like a game between two players.
Okay.
One is trying to minimize the error, and the other is trying to maximize it. They kind of go back and forth.
That sounds intense.
It is a bit, but it helps you find this optimal solution that's really robust. And what's cool is they actually show how to adapt existing algorithms, like LASSO, to use MOM. So it's not just theoretical, it's something you can actually implement.
So it's not like you have to completely reinvent the wheel to use this.
Right, exactly.
Now, how do you choose the right parameters for these MO algorithms? Like, how many blocks should you use? Is there like a rule of thumb?
That's a great question. And of course, the paper has an answer for that too. They've got this method called MOM cross-validation.
Okay.
It's similar to the regular cross-validation, but with this, MOM twist to make it more robust to those outliers. So even your parameter selection process is protected.
So you're not letting the outliers mess things up even at that stage.
Right.
Clever. Now, the paper goes into some pretty heavy math with all these sparsity equations and things like that. But then it gets back to being practical and talks about simulations and comparing these MOM methods to the traditional ones. What were some of the key takeaways from those comparisons?
The simulations showed that the Mo-based algorithms consistently did better than the traditional ones, especially when there were outliers in the data.
Not surprising.
Yeah, and even a small number of outliers could totally derail the traditional methods, while the Mo methods were like, nope, not today. They stayed stable and gave accurate results.
So it's really like MOM is this secret weapon for dealing with messy real-world data.
Exactly. It's a way to build models you can trust.
Okay, so we've seen how MOM can make things more robust in general.
Yeah.
But let's get a little more specific. How does this all play out when we're talking about like regularization techniques? Those are pretty common in high-dimensional statistics, right?
Yeah, absolutely.
And I know our listeners are familiar with things like LASSO and slope. So let's focus on those. How does MOM make those methods more robust?
Okay, so the traditional lasso and slope, they can be pretty sensitive to outliers and heavy-tailed noise. And they often rely on these kind of strict assumptions about the data, like assuming it's sub-Gaussian, which, let's be honest, isn't always true in the real world.
Yeah, real-world data can be messy.
Exactly. So by incorporating MOM into lasso and slope, you get, well, MOM lasso and MOM slope, which are much more resilient to those issues. They can handle outliers and heavy-tailed noise much better.
So M kind of relaxes those assumptions a bit, makes things more flexible.
Exactly.
And the paper like actually shows this works, right? Like there's some theoretical backing for this.
Oh, yeah, definitely. They've got these theorems that show how well MOM lasso and MOM slope perform, even when you make weaker assumptions about the data.
Like what kind of weaker assumptions?
Well, for example, they show that even if your noise only has a minimal moment where is greater than 2, these MOM-enhanced methods can still achieve, like, optimal rates of convergence.
Okay, and I'm guessing the traditional methods would struggle with that.
Oh, yeah, especially if you've got outliers in the mix. Traditional methods really rely on those stricter assumptions. And the probability estimates, the ones associated with those convergence rates, they're much better for MOM lasso and MOM slope.
So not only are they more robust, but they're also more reliable in how they perform.
Yeah, you could say that.
Now, the paper also talks about sparsity, right?
Mm-hmm.
And how that plays a role in these regularization techniques. Can you unpack that a bit for us?
Sure. So sparsity, it's really important when you're working with high-dimensional data where you have tons of features.
Right, you don't want your model to be overly complex.
Exactly. Both lasso and slope, they try to find these sparse solutions, meaning they try to identify a small subset of features that are actually important for making the prediction.
Makes sense. Simpler models are usually easier to understand, and they tend to generalize better to new data.
That's the idea. And what's cool is the paper shows how this concept called the sparsity equation, which is used to analyze lasso and slope, can also be used to analyze MOM lasso and MOM slope.
Ah, so it's like the same tools still apply, even though you've made the methods more robust.
Right. And it helps us understand how these methods achieve sparsity while still being robust to outliers. They're not sacrificing one for the other.
So you get the best of both worlds. Now, the paper doesn't just talk about theory, right? It actually gives you algorithms you can use to implement all of this.
Oh, yeah, absolutely. They provide specific algorithms for implementing MOM lasso and MOM slope. And they adapt existing algorithms like, coordinate descent and ADMM to work with MOM. So it's not like you're starting from scratch.
That's good to know. It sounds like they've really thought about how to make this practical.
They have. And they even talk about how to choose the hyperparameters for these algorithms in this robust setting. Like they propose using a MEM version of cross-validation.
So even the hyperparameter tuning is more robust.
Yeah, because the traditional cross-validation, it can also be influenced by outliers. So
Yeah.
they've come up with this MOM V-fold cross-validation procedure that's much less sensitive to that corrupted data.
Wow, so they've really covered all the bases, haven't they?
Right.
You've got the theory, you've got the algorithms, and you've even got a robust way to choose the hyperparameters. It really sounds like MOM is this comprehensive toolkit for doing robust machine learning.
It really is.
Okay, so we've covered a lot of ground here. We've talked about the theoretical guarantees, the algorithms, the hyperparameter tuning. But let's step back for a minute and think about what this all means for our listener. What are the key takeaways here? What should they keep in mind as they're tackling machine learning problems in their own work?
I think the main takeaway is that robustness really matters, especially when you're working with real-world data.
which is pretty much always, right?
Yeah, pretty much. You can't just assume your data is perfect. Outliers are out there lurking in the shadows, and they can really mess things up if you're not careful.
So what you're saying is we need to be proactive about incorporating these robust methods into our machine learning pipelines.
Exactly. And Mom is a really powerful and practical way to do that. The paper shows that it works, both in theory and in practice. It can handle outliers, heavy-tailed noise, and it can even relax some of those strict assumptions that we often make in traditional settings.
And what's really cool is that it's not just some abstract theoretical idea. You can actually use it. They've provided the algorithms, the hyperparameter tuning methods, the whole 9 yards.
Right, it's ready to go.
Now, this paper focuses specifically on LASSO and slope, but I imagine this idea of using MOM could be applied more broadly, right?
Absolutely. Think about all the other machine learning methods and algorithms out there. How many of them could be made more robust by incorporating MO principles? It's a really exciting area to explore.
It's like a call to action for the machine learning community. We need to move beyond those traditional assumptions and really embrace these robust methodologies. Because at the end of the day, it's all about building models that can actually handle the complexities and the uncertainties of the real world.
Couldn't have said it better myself.
Well said. So with that, I think we've covered a lot of ground in this part of our deep dive. In our final segment, we'll try to distill all of these findings into a concise summary, highlighting the transformative potential of median of means in revolutionizing the landscape of robust machine learning. Welcome back to the deep dive. We spent the last 2 segments really getting into the nitty-gritty of robust machine learning, especially this innovative median of means approach.
Yeah, it's a fascinating concept.
It is. So now let's take a step back and kind of synthesize what we've learned. What are the really key takeaways from this paper that our listeners should walk away with?
Well, I think the biggest takeaway is that traditional machine learning algorithms, they often just fall apart when faced with real-world data.
Right, because real-world data is messy.
Exactly. And a big part of that messiness is, well, outliers. They can really throw a wrench in the works, lead to inaccurate models and predictions you just can't trust.
So we need a way to deal with those outliers. And this paper's saying MOM is a pretty good way to do that.
Yeah, Mom offers a really powerful alternative. Instead of just being super sensitive to extreme values like traditional methods, Mom is like, let's divide things up, calculate the mean for each chunk, and then use the median of those means.
Kind of like a divide and conquer strategy.
Exactly. And it makes the whole approach way more resistant to those pesky outliers.
Okay, so that's the practical side. But the paper also gets into the theory behind it, right?
Yeah, for sure. They go deep into proving that Mama actually works.
And they have this modified breakdown point idea, right?
Mhm.
Specific to machine learning.
Right. They use it to show how much contamination a model can handle before its predictions become totally unreliable. It's like a measure of robustness, but tailored for machine learning.
Okay, so they've got the theory, they've shown that it works, but then they also give us these practical algorithms.
Oh, yeah. They show you how to actually do this stuff. Like, they adapt familiar methods like lasso and slope to incorporate Mom. So you get Mom lasso and Mom slope.
Which are more robust versions of the original.
Exactly. And
Yeah.
they still have those nice properties like sparsity. So you end up with models that are accurate and interpretable.
Which is what we want, right?
Absolutely.
And they even talk about how to choose the right parameters for these algorithms using this MOM version of cross-validation.
Right, because even hyperparameter tuning can be messed up by outliers if you're not careful. So they have this MOM cross-validation process that's much more resilient. It's like they thought of everything.
They really did.
Yeah.
And all of that leads to models that are more reliable in the end.
Exactly.
Now, one of the things that I found really fascinating about this whole approach is how, by using these random blocks, MOM sort of naturally has this built-in outlier detection mechanism.
Yeah, it's pretty cool.
Like if you've got these data points that keep ending up in blocks with really different means from the others, it's like a red flag.
It's like, hey, maybe take a closer look at these guys. They might be outliers. It's like a built-in data cleaning tool.
Exactly. So it's not just about building robust models, it's also about understanding your data better.
Totally agree. And this paper, even though it focuses on lasso and slope, it really points to a bigger picture. It's like, hey, machine learning community, we need to start thinking differently about how we build models.
Right. We can't just keep making these assumptions about our data that aren't always true. We need to be more robust, more flexible.
Yeah, it's a call to action to move beyond those traditional methods and really embrace this idea of robustness.
Because at the end of the day, we want models that can handle the real world, warts and all.
Absolutely.
So to our listener, I think the message is clear. Robust methods are the future. And this median of means approach, it's a powerful tool to have in your arsenal.
I completely agree.
Well, that brings us to the end of our deep dive. We've covered a lot of ground, but hopefully you've all come away with a better understanding of how median of means can revolutionize the field of robust machine learning. And to recap, just to make sure the key points really stick, traditional machine learning algorithms, they're often very sensitive to outliers. This paper introduces median of means, MOM, as a way to make those algorithms much more robust. It provides a bunch of practical algorithms you can use, like MOM lasso and MOM slope, and it also shows how MOM can be used for things like hyperparameter tuning, using a robust version of cross-validation. Overall, MOM is a really exciting development in machine learning. It's a way to build models that are more reliable, more accurate, and ultimately more useful in the real world. So thanks for joining us on the deep dive. Until next time.